Today we are going to discuss about the linkage disequilibrium. This is the topic on which you will not find many videos. And since I am a professor in a university and I am teaching this subject and getting lots of requests to make a video on linkage disequilibrium, this video I am making for my own students as well as for the students who are preparing for any competitive exam. But you need to watch this video till the end so that you can understand the basic of linkage disequilibrium. You will also understand if there is a linkage, whether it is going to make any significant impact or not, and how you can calculate the linkage disequilibrium population. Without doing any delay, just start the videos and kindly watch this video till end so that you can understand the basic. So let's see the linkage disequilibrium. Linkage disequilibrium. So you might have heard about meiosis. In the meiosis, there is a recombination in between the two homologous chromosomes. Suppose this is your homologous chromosome, and the students who are confused about the homologous or the non-homologous chromosome, they can watch my video on the mitosis and they will clearly understand what are homologous and what are non-homologous chromosomes. So let's say these are your homologous chromosomes, and there are certain genes on these homologous chromosomes. Let's say if this is A1B1, this is A1B1, this is A2B2, and A2B2. And these are the homologous chromosomes. These are the homologous chromosomes. Now, if there is any recombination, what will you get? Can you make the structure out of it? If there is any homologous chromosome, you will see like this. So if suppose this is A1B1, this is A1B1, this is A2B2, this is A2B2. So now at this position you can see, if you see at this position, the recombination is taking place at this position. Right? So this is the recombination which is taking place. Now if there is a recombination, what will you get out of it? You will get the chromosome which is like A1B1. Then you will get the gamete which will be having A1 and B2. You will be having the gamete which will be having A2 and B1. And you will be having the gamete which is A2 and B2. And this is clear from this. You can see A1 and A2 are exchanging from each other. B1 and B2 are exchanging from each other. So in place of A1, there will be A2. So you will get A2 B1. Similarly, here the B1 and B2 are exchanging the DNA material between them. So here B2 will come. Let me highlight this portion. You will see that the B2 will come here and B1 will go here. So you will get A1 B2, right, and A2 B1. So if you see here, what are the recombinants? If you see here, and I'm so sorry, I don't know the editing part, so I can't edit my videos. So please beware of this. So A1 and B1, these are the non-recombinants because they are the parental type. These are the non-recombinants. Can you tell me what else are the non-recombinant gamete? Is the A1 B2 is the non-recombinant gamete? No, it's a recombinant gamete. What is A2 B1? This is the recombinant gamete. And what is A2B2? This is the non-recombinant gamete. Okay. So here you can see, if we follow the Mendel's law, because every gene independently is sort according to the Mendel's third law. So what will happen? The frequency of the non-recombinants and the frequency of the recombinants is equal. So according to Mendel's law, the frequency of non-recombinants is equal to frequency of recombinants. This is the Mendel's law. So here the frequency, because the overall frequency cannot be more than 1. So it will be like 0.25, 0.25, 0.25 and 0.25. This is according to the Mendel's law. But Mendel's law is not always followed. And one example is the linkage. If suppose the genes are linked, for example, let me highlight this. If suppose the genes A1 and B1, they are located very close to each other, then there won't be any recombination. So the formula of the recombination is like this. If they are located very near to each other, the recombination will not take place because the genes are linked. So let me write this point. It's an important point. If genes are located near to each other, they are linked. They are located near to each other, then they are considered as linked genes. Then what are they? They are linked genes. They are the linked genes. And when they are linked genes, it means there won't be any recombination. So what does it mean? It means there won't be any no recombination, or you can say very less chances of recombination, depending on the distance between the genes. Okay. So this is known as the linkage disequilibrium. In case of the linkage disequilibrium, genes are located near to each other, so the chances of recombination becomes less, and the frequency of the gametes that is going to be formed in the meiotic phase is not going to be equal to 0.25, 0.25, 0.25, 0.25. It will vary, depending on the distance between the linked genes, whether they are located near to each other or very near to each other. Depending on the distance between the genes, the frequency of these gametes which are going to be formed in the meiotic phase is going to vary. So this is known as the linkage disequilibrium. So always remember, in case of the linkage disequilibrium, Mendel's law is not going to be followed. Now let's come to the another point, how to calculate the linkage disequilibrium. So how to calculate linkage disequilibrium? Is the formula is this: the frequency of non-recombinants minus frequency of recombinants. This is the formula of the linkage disequilibrium, where D is the linkage disequilibrium. D is what? Is the linkage disequilibrium. Means the frequency of the recombinants and the frequency of recombinants is not going to be equal. In this case, what you can understand, in case of the linkage disequilibrium, frequency of recombinants is not going to be equal to frequency of non-recombinants. Okay, and another formula which you need to understand is the frequency of recombinants plus frequency of non-recombinants is going to be equal to 1. And always remember, the frequency of the non-recombinants is most of the time is high because they are parental type. For example, in my previous slide, if you go to my previous slide, A1, B1 and A2, B2, these are the parental types. So the frequency of these non-recombinants, the chances of the non-recombinants is going to be high in comparison to the frequency of recombinants in case of the linkage disequilibrium I am talking about. Okay, so that's how you can calculate the linkage disequilibrium. Now understand this with the with an example. Let's understand here only. Let's say there are two blood group Mn and SS, and suppose this is M, this is N, this is S, and let's say this is a small s, and we can make it really small so that we can understand. So now MS, if you make the Punnett square, where it is going to be NS, then this is going to be equal to M and then small s, okay, and this is going to be equal to N and small s. So what are the parental types? These are the parental types. So what are the parental types? This and this are going to be the parental types. And what are the non-parental types? This, no, it's not a good color actually. These are the these are the recombinants type. So if we see here, so we can say M and S and N and S. These are the non-recombinants type or the parental type. Usually in case of the linkage disequilibrium, frequency of these non-recombinants, because they are the parental types, is going to be higher. But let's say these are the non-recombinants type. Okay, then N, S and M and S, these are the recombinants type. Okay, and if I say in the question, if it is giving that you are having the individuals which are having the blood group M and S out of 1000 pupil, if let's say if it is like 474, then coming to an S, let's say this is 611, and let's say if this is an S, let's say this is 142, and this is MS, let's say this is 773. So what will happen in this case? In this case, you can calculate the frequency of M and S. So it is going to be, as you can calculate, it is going to be 474 divided by 1000. Similarly, it is going to be 611 divided by 1000. This will be 142 divided by, sorry, 2000, or 1000, it is 2000, let's say. 142 divided by 2000, and then this is 773 by 2000. Okay, so if you calculate this, and let me rub this this part actually. Okay, so if you calculate 474 divided by 2000, that is going to be equal to 0.2370. I have already calculated with my calculator, but you can actually calculate it. Then N and S, this is 611 by 2000, so that is going to be equal to 0.3865. Then this is going to be N and S, capital one. This is going to be equal to 0.3050, and then is going to be equal to M and small s, which is going to be equal to 0.0710. So one thing which you need to understand, MS, these are the non-recombinants. First of all, you need to find it out which are the non-recombinants, and N and S, these are the non-recombinants. and this is going to be recombinants. Okay, now you can calculate the frequency or the linkage disequilibrium. So let me rub this also now. So you can calculate the D, which is equal to the frequency of non-recombinants minus frequency of the recombinants. So non-recombinant frequency is going to be equal to 0.2370 into 0.3865, which is this one, because these are the non-recombinants one, and then it is 0.3050 into 0.0710. When you calculate it, it will be coming something like 0.07. So this is going to be your linkage disequilibrium. So now you know this is going to be the linkage disequilibrium. Now if the question is coming how much percentage of the linkage disequilibrium is there, then in that case you need to calculate the D max value. In that you need to calculate the linkage disequilibrium, which can be at the highest level. So how will you calculate the D max? As you can understand in this formula, let me highlight this. If this is going to be very less, one second, this if this is going to be very less, then in that case D is going to be high. You can simply understand this by the math. For example, if I say D is like 0.5 and this is like 0.1, then it is this value is going to come to 0.4. But if I say, if I am decreasing this value to 0.05, then what will you get? D is going to be equal to 0.5 minus 0.05, then you will get the more value. Similarly, if you are again decreasing this value, you will get the maximum D value. So the maximum D value is you can get whenever the frequency of the recombinants is less. So what you can see here, you can see the frequency of the recombinants. If this is less, you will get the D value, which is going to be higher, and you can do it by the simple math. You just decrease this value from 0.1 to 0.05, you are getting the high D value. If you are decreasing it further, you will get the more higher value than this value. So the formula is like this, that the frequency of the recombinant, if it is less, you will get the D max. And the D max calculation formula is, which you can memorize basically, is going to be the frequency of recombinants plus D. So in this case, if you see the frequency of recombinants is, in case of the NS, if we talk about, it is, what is the frequency? 0.3050 plus D, which you get 0.07. So this is going to become coming something like 0.3750. In case of the M and S, which is again the recombinant, you will get the value is like 0.07 plus 0.07, and you will get the value of 0.14. So you are getting two values for the two recombinants. Okay, one is the recombinant NS and the another one is the recombinant which you are getting the M and S. Can you tell me 0.14 is higher than 0.37 or 0.14 is lesser than 0.37? Simple question, but let's say, so definitely the 0.14 is less than 0.37. So your D max is going to be equal to 0.14. So now if I am asking you the question, you have the D max value here right now, which is your 0.14, and you have the D value which is like 0.07. Can you calculate the percentage? You can calculate. So out of 0.014, if it is like 0.07, so out of 100, how it is going to be? 0.07 divided by 0.14 into 100. if we do the simple calculation, it is going to be 50%. 50% of your population is in the linkage disequilibrium for the studied genes. Whatever the genes you are studying, then you can say that in the 50% of the population, these genes are actually linked. And this is very important in genetics. If the genes are linked, they can have a different impact, at least in the future generation, because they are all linked. So they will be like carrying in the same way, they won't be segregated, and in the one gamete you will get the both genes, and maybe in the another gamete you may not get it. So because they are the linked genes, there won't be any recombination. So the ultimate effect is going to be on the future generation. For example, if two of the genes are basically linked, they will pass on like that to the future generation. There won't be any recombination. So this is like the linkage disequilibrium, how you can calculate it. Now I just want to summarize it. In case of the blood group Mn and Ss, you can see the recombinants. These are the recombinants, Ns and Ms, and these are the non-recombinants. And if suppose the number of individuals are giving, you can calculate the frequency, which is like 474 divided by total number of individuals which you are studying. Let's say if it is 2000, you can calculate it. So here you will get these values. Okay. Now the formula of D is the frequency of non-recombinants minus frequency of recombinants. As you can see here, if you decrease this value, you will get D. The value of D is going to be higher, but in this case you can calculate the D, which is the frequency of non-recombinants, which is this one. You can calculate it 0.2370, 0.3865 minus frequency of the recombinants, which is 0.3050, 0.0710, and it is going to be 0.07. Now you need to calculate the Dmax. So for calculating the Dmax, the formula is frequency of recombinants, and you add the value of D in that. So frequency of recombinants is 0.3050. You add the D value 0.07, you will get this value. Then similarly, the another recombinant frequency is 0.07. You add the D value in this and you will get the 0.14. And the 0.14 is lesser than 0.37. So D max is going to be equal to 0.14. Now you know the D max and D value. So out of 0.14, if there is a 0.07, so out of 100, how much? So you can simple mathematics it is, you will say that you are 50% of the population. In 50% of your population, your studied genes are going to be linked genes. Now coming to the linkage logs of odds ratio, which is the LOD ratio. And this is very important. If suppose the LOD ratio is going to be more than or equal to 3, you will say your genes are significantly linked. Genes are significantly linked, and this thing you need to understand also. These genes are significantly linked. But in case of the LOD, if it is coming like less than 3, then you can say that the genes are not significantly linked. Not significantly linked. And the word significant is very important. The value of significant is when the p value is equal to or less than 0.05, then this is known as the significant value. What does it mean? It means the chances of the probability of chances is only 5%. If suppose there are 10 coins, and what are the chances that you will get a specific coin, and if the p value is coming less than 0.05, then you can say the chances, the probability of chances is only 5% that I will get this coin. Otherwise 95% chances are there that I will get the other one coin also. This is just an example. So it means whenever the p value means a significant value or the probability, the chances are only 5%. Like you are, if suppose you are buying a lottery ticket, and every time 95% of the chances you are not getting anything. So you can say 95% of the chances are there. 95% is the probability that I won't get anything, but the 5% there are the chance that I may get it. The chances are chances of probability, chances of the event. Chances of the event is only 5%. 95% you are sure. What does it mean? 95% you are sure about the results. Only 5% you can say ki, there are chances that I will get this error. There may be error, but 95% there won't be any error. So this is the significant, the p value, which is a significant value. It's a very important. If you see the clinical trials also, they always consider, they give their drug, they compare their drug with the standard drug, and if the p value is coming less than 0.05 in case of the overall survival or disease free survival or progression free survival, they will say their drug is doing a good job in comparison to the standard therapy. So how will you calculate the LOD ratio? So first thing is this: if suppose in a question, if it is coming, how much should be the LOD ratio for saying that the genes are significantly linked, it is always going to be more than or equal to 3. If it is less than 3, the genes are not significantly linked. So now let's do one numerical out of it. If suppose in the numerical you have been giving that the frequencies of the recombinants is 0.1, can you calculate the frequency of non-recombinants? As you know, R plus NR is equal to 1. So NR you can calculate 1 minus R, which is 1 minus 0.1, which is 0.9. And how many non-recombinants you are getting? No, how many? Because in the meiosis you are getting 4 gametes. You are getting 4 gametes. 2 are the non-recombinant and 2 are the recombinant type. Okay. So in that case, this is the non-recombinant gamete. Hai na? So then what is the frequency of the one non-recombinant is going to be half of this 0.9 by 2, which is 0.45. Because whatever you are getting here, this is for the 2 gametes. For 1 gamete, it is going to be, again you need to divide it by 2. So this is going to be 0.45, right? And the frequency of recombinants is like 0.1. Then in that case, you can also say it is going to be 0.1 by 2, which is equal to 0.05. So these are the things which you need to understand, because in the meiosis you are going to get 4 gametes. 2 are the non-recombinants, 2 are the recombinants. Whenever they are saying the frequency of recombinants, they are talking about 2 gametes, not just 1. Remember this. So you need to calculate the frequency of 1 recombinant. You know the frequency of 2 recombinant. If it is 0.1, then the frequency of the 1 recombinant is definitely going to be 0.05 here and a 0.05 here. And if you plus it, then it is going to be 0.1. Similarly, if it is like 0.45 here, 0.45 here, if you plus it, you will get the 0.9. Okay. So now coming to the LOD ratio. What is the probability of the genes that are linked? Probability of genes that are linked and probability of genes which are not linked. So probability of genes that are not linked. So if they are not linked, the frequency is always going to be equal for the recombinants and the non-recombinants one. When there is no linkage, the frequency, remember that when there is no linkage, the frequency of the non-recombinants is always going to be equal to the frequency of recombinant. It is always going to be 0.25, 0.25 for the non-recombinants and the 0.25, 0.25 for the recombinants. Okay. So let's say if suppose in a family you are getting 8 recombinants and 0 non-recombinants, or maybe I should say the other way around, which basically uh, so you can calculate here. Yeah, now you know. So let's calculate it. So now you know the frequency of non-recombinants is 0.45, right? So you need to write here 0.45, and how many non-recombinants you have? 8. Now the frequency of recombinants, which is going to be equal to 0.05, and how many you have? 0, divided by frequency of non-recombinants, and frequency of recombinants is going to be equal, so it will be like 0.25 and 0.25, and 1 to the power 0 is equal to 1. So you will be getting like 0.45 into 8 divided by 0.25 into 8, and you will see the value is not more than 3. If it is not more than 3, you can say the genes are not linked. So just to clear this phenomena one more time, let me highlight this. If suppose in a question, if R is giving, means the frequency of recombinants is giving, let's say 0.1, then they are talking about 2 gametes, they are not talking about 1 gamete. You need to calculate it for the 1 gamete, which is going to be 0.05. Then you need to calculate the frequency of non-recombinants, which is equal to 0.9. Again, this is the 0.9 is for the 2 gametes, so you need to calculate it for the 1 gamete, which is equal to 0.45. Now the formula is like this: frequency of the non-recombinants into frequency of the recombinants divided by, when the genes are not linked, the frequency of recombinants and non-recombinants is always going to be equal to 0.25, 0.25, 0.25, 0.25. So here the frequency of non-recombinants, what we have calculated, the NR is 0.45. So we will write 0.45, and how many non-recombinants? 8. So we will write 8 here. Now the frequency of recombinants, how much is the frequency of recombinant? 0.05. How many other recombinants? 0. So we'll write 0 here. Frequency of recombinants and non-recombinants is always going to be 0.25 when the genes are not linked. Okay, they will follow the Mendel's law. Then again, the non-recombinants is 8 and 0. You will calculate it. If the value is coming less than 3, you will say the genes are not linked, whatever the genes you are studying here. So I hope I make this lecture clear to you, and I hope you learned this lecture. You have watched my lecture from starting till end, and if you like my this content of this lecture, please subscribe my channel, and I will make other videos like on other topics as well. And if you have any question, please write in the comment section, and I would be happy to answer you. Thank you so much.